Class example 1.5.1 is an important question. It's going to take us a little while because we're going to do a couple of different methods for some of these more trickier questions. Some of them we're going to use the systematic perfect squares, perfect cubes list, and we will go from there. What is meant by simplifying the following? Now, does it mean just chuck it into your calculator and find out what the decimal answer is? No. When we simplify a radical, we want to get it into its simplest form, meaning that there are no perfect squares or perfect cubes or fourth roots underneath the radical sign so that we can eventually perform operations on them. So we're going to start with a list of the perfect squares. And then we're going to make a list of the perfect cubes. And we'll leave those two on here as we're working through our examples. Now, perfect squares, we know 1 squared, 2 squared, 3 squared, 4 squared, and we can keep going. 5 squared, 8 squared is 64, 81. What do we got? 100. We've got 121 and 144 for the perfect squares. Perfect cubes means you're taking that number and multiplying it by itself 3 times. So 1 times 1 times 1. 2 times 2 times 2, 3 times 3 times 3, 4 cubed, 5 cubed is 125, 6 cubed is 126, the 7th perfect cube, the 8th perfect cube, we've got the 9th perfect cube is 729, 10 times 10 times 10 is 1,000, 11 times 11 times 11, and let's finally end with 12 times 12 times 12. Now, we'll start looking at the square root of 75, and we're going to use a method that I like to call the perfect squares method. We're going to try and find the largest perfect square that will evenly divide into 75. So we're almost looking for we're looking for a factor of 75 that happens to be a perfect square. The way that I like to do this is I like to start at the bottom of my perfect squares list. I'm going to go up to where 75 kind of fits in. So 75 fits in between 64 and 81. So potential factors of 75 are 1 through 81 on the perfect squares list. Now I can see that 64 is not going to evenly divide into it, but you could try it. You could say 75 divided by 64, and when you do that, you're going to get some ugly decimal. Yep, there it is. We don't care too much about it. That should be a 9, sorry. So I'm going to try 49. I'm going to take 75 and I'm going to divide 49. So one of our additional systematic processes for factoring that we're actually going through, but this time I'm particularly picking my factors that I want, and I'm starting with the high numbers instead of the low numbers. I'm going to try 36. 75 divided by 36. Nope, that doesn't work. But 75 divided by 25. We can see that that's a nice number. So I know that 75, I'm going to keep it underneath the square root symbol. Sorry about that. Could be the same thing as saying 25 multiplied by 3. Now notice I've put the perfect square at the beginning here. And then I put that multiplication sign of times by 3 because we know 3/4 is 75. Okay, so we're okay with that. Next thing I'm going to do is I'm going to break that radical apart. I can say that the square root of 25 times 3 is the same thing as the square root of 25 multiplied by the square root of 3. But we already know that the square root of 25 is the 1, 2, 3, 4, 5th perfect square, so I could write that as a nice 5 multiplied by the square root of 3. So notice I'm just taking a breakdown of 75 into 25 and 3, a breakdown of the radical into 2 separate radicals. I'm finding the nice perfect square of the number that came from my perfect squares list and multiplying it by the remaining radical. And then our very final step, which you could probably skip this second one here. You could probably skip this one here too and just break it down into these two. I can actually rewrite this as 5 square root of 3. Now what 5 is called the coefficient. And then we've got the radical or the square root of 3. Similarly to in math 9 and math 8, if you had 5 times x, or if you had 7 times a, or if you have, I don't know, -2 times y, those numbers are what we call the coefficients, and then we've got a, x, and y as variables. Well, in this case, 5 is still a coefficient, but the root of 3 is now a number instead of a variable. It's just an irrational number. So I'm taking 5 and multiplying it by the root of 3, just like we used to take 7 and multiply it by a. Okay? And we keep this as a nice exact form because if you actually put the square root of 75 into your calculator, you get 8.6602540339, blah, 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 blah. It is an irrational number. We like to keep things nice and neat and tidy just for rounding rules and for operations like adding and subtracting, which we're going to do a little bit later on. So the square root of 75 simplifies down to 5 multiplied by the square root of 3. Okay, let's look at the fourth root of 288. Our list here is perfect squares and perfect cubes. We're not going to do a list of perfect fourths roots. Instead, we're going to use that prime factorization method. So we're going to take 288 and we're going to break it down into prime factorizations here. Now we can go with our systematic method. I see 288 is even, so I could divide it by 2, or I could take another number. I'm going to take another even number, and I think it was the same number I randomly chose before. I'm going to take 18. And when I take 288 and I divide it by 18, I actually get 16. So I'm going to keep breaking this down a little bit further. They're both evens, but I know that this is 2 times 9, which is 18. So I can square up my 2 here. And I know that 3 times 3 is 9. Working both arms of my factor tree, I can say that 2 times 8 is 16. I know that that's 2 times 4. And then I can break that down into 2 times 2. So we have a prime factorization of 2 times 2 times 2, 1, 2, 3, times another 2 and another 2, and then I got a couple of 3s. Okay. Before, when we were looking for perfect squares, perfect cubes, perfect fourth roots, we were looking for even groups, depending on what the index was. This time, I've got a fourth root, so what I need is 4 perfectly even groups of what I've got in my prime factorization to figure out, is there a perfect fourth root that can actually divide evenly into 288? Now, I can already see there's not 4 3s, so we're going to have what we call as the leftovers here, okay? So I can see I've got 1, 2, 3, 4 2s, so at least I can put 4 2s in each one of those fourth groups. And I can see I've got some leftovers, so I can rewrite this as 2 times 3 times, oopsies, that's a 3 times 3. So I'm still multiplying all these numbers together. I've just rewritten it out a little bit differently here, okay? So what we're going to do is we're going to take 2 times 2 times 2 times 2, 4 times, and I'm going to get the number 16. I'm going to write that out by these numbers over here, which is 2 times 3 times 3, which is 9, 18 over here. Ooh, ironically, that's the very first 2 that we had. And what we're going to do is we're going to go and now use the fourth root of 288, and we're going to similarly break it down how we did before. So I am going to take the fourth root of 288 and break it down into the fourth root of 16 times the fourth root of 18. I am then going to break this apart into 2 separate fourth roots with a multiplication sign in between, the fourth root of 16 and the fourth root of 18. And in this particular case, though we know that 2 times 2 times 2 times 2 is equaling to 16, therefore the fourth root of 16 must equal to 2, right? We've got 4 of them there. So if I'm taking what number multiplied by itself 4 times equals to 16, that's a 2. So I can actually say the fourth root of 16 is 2. And then I'm leaving the fourth root of 18 as the leftovers. There's no other fourth root that comes nicely out of that. We would have seen it in our patterns here. So we can now say our final answer for the fourth root of 288 is 2 multiplied by the fourth root of 18. Okay, let's look at the cube root of 1,715, and we're going to go back to our original method. It's kind of faster, to be honest. Fourth roots are a little bit trickier because you have to have 4 even groups, and we don't have a list. We could create one, but we'll go back to let's try and find a perfect cube in our perfect cube list that factors evenly into 1,715. So I can see 1,715 kind of fits in between the cube root of the 11th and 12th perfect cubes. So we're going to go in here and we're going to say We'll go with the next smallest number. So 1,715, I'm going to divide out 1,331, and I'm going to see if it's a nice factor. It's not. We can eliminate it off its list. I can also quickly eliminate 1,000 off of its list because we know it's not going to have any zeros at the end. So I'm going to go with 729. So I'll take 1,715 and I'm going to see if 729 evenly divides into it. Nope, it doesn't. It's still an irrational number. So I'm going to move up the list systematically as we've done in the past. 1,715 divided by 512. Nope, not quite. Let's move up to 343. I'll take 1,715 divided by 343 and I get 5. So that worked out nicely. So I'm going to rewrite this as the cube root of 343. Notice that I put the perfect cube first, and then I put 5. Because I know, and you could double check, 343 multiplied by 5 is going to get us back to 1,715. So what we've done is we found two factors of 1,715, but one of our factors we intentionally made a perfect cube by finding it off of our perfect cube list. Then I can rewrite this as the cube root of 343 multiplied by the cube root of 5. Now we know that that cube root of 343 was the 7th perfect cube. So I'm going to rewrite that as a 7. We're still multiplying that as the cube root or by the cube root of 5. And like we had for the square root of 75, 7 now becomes our coefficient. And this time we make sure that that 3 is really indicated as an index and really up high and small so that people don't get mistaken and say that this is 7 times 3 root 5, because that's not okay, right? That's a totally different number. That would be the same thing as saying 21 root 5. If you put 7 multiplied by the cube root of 5 into your calculator and compared it with 21 multiplied by the square root of 5, totally different things. So make sure that that 3 or that index there is up above. So we can say the cube root of 1,715 simplifies to 7 cube root of 5. Okay, square root of 30. We're going to go to our perfect squares list because this one's kind of nice. Maybe it's nice. I don't know. We're going to see. But I know that 30 is in between 25 and 36. So I'm going to start on my calculator by taking 30 and dividing by 25 to see if I get a nice even factor. I don't. So I'm going to keep going up that list. I'm going to take 30. I'm going to divide it by 16. I can see 30 divided by 16 is not a nice even factor, so I'm going to move up to 9. 30 divided by 9 is 3.3 repeating. Again, doesn't work. I'm going to go with now 30 divided by 4. Oh no, none of my perfect squares in this particular instance divided evenly into 30. So because no perfect square, and 1 doesn't count, we know anything times itself is just 1, but any of these perfect squares that are less than the actual number itself do not divide evenly into 30. Therefore, 30 is already simplified. Sorry, the square root of 30 is already simplified. Right, another fourth root. Let's go with the fourth root of 32. I don't know why, but I tend to always use prime factorization as the fallback for the fourth roots, and it's because I'm not as familiar with that list. To be honest, I don't even know what 5 times 5 times 5 times 5 is off the top of my head without thinking about it. So instead, I'm going to prime factor and see if I can get some nice even groups. Now I can see 32 divided by 2 is already going to break it down into 2 and 16. So I have 1 prime already. I'm going to break it down into 2 and 8. 2 primes, I'm going to break it down into 2 and 4, 3 primes, and I'm going to break it down into 2 and 2. I've now got 5 primes. So if I am looking for the fourth root, I am looking for 1, 2, 3, 4 even groups that I know will multiply exactly to themselves or exactly the same in order to get to a fourth root or a perfect fourth number. And so in this particular case, I also am going to have leftovers because I have my prime factorization is 5 2's. So for us, 4 of them are nice and even. This fifth guy doesn't have a partner though. So I always kind of call them the leftovers, right? So going back to our method that we had before, I could rewrite this as 2 times 2 times 2 times 2. Ironically, 16. It was the same as when we did the fourth root of 288. But this is 16 times 2. These four group together and this one, and that multiplies up to 32. So if I have the fourth root of 32, I can rewrite that as the fourth root of 16 multiplied by 2. I know that the fourth root of 16 can be broken apart from the fourth root of 2. And then, just like we did before, 2 times 2 times 2 times 2 equals to 16. Therefore, the fourth root of 16 must back equaling to 2. 2 becomes our coefficient, and we get the fourth root of 2 that doesn't simplify any further, just like our square root of 30, and this is our final answer. So we have the fourth root of 32 simplifies down to 2 multiplied by the fourth root of 32. Okay, last one here, we've got the cube root of 40. Now I have the cube root lists here already. I can see 40 is right in between 27 and 64, so I really only have two numbers to test because one is not going to be helpful to us. So I have a sneaking suspicion that the cube root of 40 is already simplified, but let's double check. Let's take 40 and divide it by 27, which is the third perfect cube. That does not turn out to a nice factor. So let's take 40 and let's divide it by 8, and I get 5. Ooh, that's lucky. So I can actually say instead, the cube root of 40 is the same thing as the cube root of 8. Notice I put the perfect cube first, multiplied by the cube root of 5. Then I'm going to break that part into the cube root of 8 multiplied by the cube root of 5. So I was wrong. It was not already simplified. I know the cube root of 8 is the second square root. The second cube root. And I can multiply that by the cube root of 5. And again, let's just be very careful that we overemphasize the coefficient, the index, and then the root itself. So we can say the cube root of 40 is equaling to 2 cube root of 5.